Part 2.
This is a result of changing flux through a loop. All right? You get voltage when flux changes through a closed loop. That's what this says. This is Faraday's law, right here.
That's very, what? Okay.
This is Faraday's law. This is Lenz's law. Just the negative sign is Lenz's law. That, the whole thing, is Faraday's law.
If Faraday determined that, why is the unit current capacitance variance?
No idea. No clue. I don't know who even does that.
Who does what?
All right. So listen. A voltage is created when flux changes through a closed loop. If that loop happens to be a conductor, current will flow in it as a result. In what direction will it flow? Notice. Look at this. Every single time that I pop a magnet into this coil, if it's increasing, boom, it deflects right, doesn't it? Boom, the other direction, it goes the other way. Right, left, right, left, right, left, you're right, you're left, you're right, left, like that, right? Okay? That's how it works. Sorry, I couldn't. Now, you guys, that will always happen. It's up to us to be able to understand how that works. All right? And that's what I want to show you with Lenz's law. That's what I want to show you. So check this out. I'm going to use we're going to pretend for a moment that this is a conducting loop. All right? And I want to present to you a hypothetical situation. This is a hypothetical situation. What I'm going to do is I'm going to take the north end of a magnet and I'm going to insert it into this conducting loop, and I'm going to observe that current flows around in this direction. That would be counterclockwise to you, wouldn't it? That would be clockwise to you, wouldn't it? Right? So, let's pretend that happened for a moment. I push this north side of a magnet into the closed loop, and EMF is generated, and because it's a conductor, current flows in this direction. Everybody okay with that? All right. Watch what happens. You guys, this thing is minding its own business. Nothing's happening. It's just a loop of wire. When suddenly, someday, this magnet approaches it, and it produces current, according to Faraday's law, because there's changing flux through it. So charges begin to move in it. Well, you guys, what does Ampere's law say about a current-bearing wire? What does Ampere's law tell us accompanies any current-bearing wire? Can you say that louder?
Produces a magnetic field.
One more time.
Produces a magnetic field.
It produces a magnetic field of its own, doesn't it? So watch this. Think about this. Magnetic flux increases, creating current. That current produces its own magnetic field. Our second right-hand rule says if we put our thumb in the direction that that current travels, the magnetic field wraps around the wire, doesn't it? Well, that's producing more magnetic flux through the loop in that direction. That's going to generate more current flowing in this direction, which produces more magnetic flux in that direction, which produces more current. And eventually, I got to set this thing down because it's so darn hot. It's an infinitely energy-creating device. And we know that doesn't happen, does it? We know that doesn't happen. I can't take a loop of wire and add a magnet to it and then have it produce all kinds of energy for me. That violates what? The conservation of energy. So, what has to happen instead is this. Listen carefully. The induced current that flows in a conductor must be in a direction such that its magnetic field opposes the changing flux that created it in the first place.
So it can't
can't do it. It's got to oppose
Oh, that's
the changing flux that created it in the first place. Now watch. Easier said than done. And I'm going to write that down, by the way. What I just recited to you was Lenz's law. And I'm going to write that down in just a minute. All right, I'm going to write that down in just a minute. But what actually has to happen is this. Look, this is what really happens. This guy minds his own business. He's not doing anything wrong. He's just sitting there. Nothing's going on. North side of a magnet comes in. Current begins to flow. But current has to flow in a direction such that the changing flux that created it is opposed by the magnetic field generated by that induced current. So watch what happens. Increasing flux in this direction. Lenz's law says there better be a magnetic field to oppose that increasing flux. So I put my hand in the loop, literally in the loop, and then I can grasp it, and my thumb will point in the direction that the current actually flows. So I'm actually using the second right-hand rule backward. I'm putting my fingers, my magnetic field lines, in the direction that I want. I curl my fingers, and my thumb points now in the direction that the current actually must flow in this loop. Hold on there, fella. I'm going to write this down, and then we'll do a billion more examples. Watch this. Watch this. This is Lenz's law. This is what Lenz's law says. Whew. Lenz's law says the following. An induced current will flow in a direction such that its magnetic field opposes the changing flux that created it in the first place. Now, let's apply that thing. But I'm going to give you a few minutes to jot that down because that's huge. That's important and big. That's the conservation of energy for Faraday's law. I'm going to show you this. Oh. Watch. Look at this. You're going to accompany Lenz's law with two questions. The first question is this. Is flux increasing or decreasing? That's a pretty simple question to answer. You guys, watch this. If I introduce the north side of a magnet to a loop, are more magnetic field lines or fewer magnetic field lines making it through the loop? More or less? More. So with this question, it's increasing. If I withdraw the magnet, are more magnetic field lines or fewer magnetic field lines making it through the loop? Fewer. In that case, it's decreasing. It's easy, isn't it? The next question. In what direction is the flux increasing or decreasing? Now, that's an equally simple question to answer, because the answer to that is merely the direction of the B field. Okay? You have to combine those two things. Watch. If I take my loop and I add a north side in, what I'm going to say is that flux is increasing in that direction. Why? Because north poles go away from north and towards south. Right? Look at this. If I push my south pole in, it's increasing. but it's increasing in that direction. Because the magnetic field lines are towards south, aren't they? So this question is simple. It's just the direction of the magnetic field. This one's simple because it's, are more magnetic field lines making it in or are fewer? It's as easy as that. Okay? Now watch. Watch this. If I take a loop and I push it into a magnetic field like that, that's the same question. Let's determine in what direction, clockwise or counterclockwise, the current will flow. Watch how to do this. First, if I'm moving this loop into a magnetic field, is flux increasing or decreasing? In what direction is it increasing? Into the board, right? Lenz's law says we want to oppose the increasing flux. How do we oppose increasing flux in that direction? By adding magnetic field lines back in the other direction. Back through the loop like that. I'm going to do that, and now I'm going to grasp the loop, and my thumb points in the direction that current actually flows. Current is actually flowing in this. When I'm moving it toward it, it's going to be moving like this. Current is going to flow around like that in a conductor. Watch this now. This is key. The whole key to this is opposing the changing flux. Opposing the change. Look what we did there. Flux was increasing this way. I want to oppose that by increasing it the other direction. Right? Now look. If I continue this now so that the loop is now fully in the field, there's no changing flux, there's no induced current, there's no induced magnetic field. Now if I keep going, if I now keep moving it so that it's coming out of the field, watch the difference. Look at this. Is flux increasing or decreasing? Flux is decreasing in what direction?
Into the board.
In the direction of the magnetic field. It's still in this direction, but now it's decreasing in that direction, isn't it? Lenz's law says we want to oppose that decrease, don't we? We want those magnetic field lines back. We want to oppose the decrease by adding flux through the loop in that direction. You see that? So now I grasp it, and now it's going to go that way. It's changed directions. Now it's going to go this way. You see that? Yeah.
How does it go that?
Because look, the flux is decreasing through the loop in this direction. Lenz's law says we want to oppose the decreasing flux by adding flux in that direction. It wants them back. So now you grasp it, and your thumb points in that direction. Right? You can put your hand in here and grasp it from any side you want. I can't grab it with the back of my hand. It's painful. Yeah?
Would there eventually be like nothing?
That's your left hand.
What?
I'm just saying that's your left hand.
Oh, I'm not using the right.
I know, but I'm just saying that's your left hand. Okay, what?
Okay, so then when on the other side, it just happened the same thing, so just keep going back and forth.
Yeah. Yeah, it's gonna start off, current's gonna flow like this, it's gonna stop, and then it's gonna flow like that.
If the loop was parallel to the magnetic field, nothing would happen because there's no flux through the loop, right?
If it was like this,
Yeah.
zilch choke.
Okay.
No, not a. Hey guys, when you apply Lenz's law, you want to oppose the changing flux. That's big. Jay, you with me? Okay. Because let me tell you something. If flux is increasing, you want to oppose it by putting your fingers in the other direction. If it's decreasing, you want to oppose the flux by adding it in the direction that it's going. So you're opposing the change. Now let me show you something. This copper tube over here, this copper pipe, it's non-magnetic. It's non-magnetic. Let me show you why. This is copper. This is a very strong magnet. Non-magnetic, right? If I hold this vertically, this copper wire can be thought of to be infinite number of little coils, loops, stacked one on top of the other. Okay? So let me show you this. If we drop, here's my coil. Here's one coil. If we drop a magnet, the north end of a magnet in here like this, watch this very carefully because I'm going to show you this demo that's going to stun you. Okay? If I introduce this north end to a loop like this, let's apply Lenz's law to it. Okay? Is flux increasing or decreasing through the loop?
Increasing.
It's increasing. It's increasing in that direction, right? Lenz's law says we want to oppose that increase by adding flux back in this direction. I grasp it, my thumb points like that. So the current is going to flow like that. You guys got that? Now, think about this. Think about this. If I've got my thumb in this direction, that means that this is going to create like a little mini North Pole here to oppose the motion of that North Pole coming down through the loop. It produces a little mini North Pole here like that, saying, hey, stop it. So think about this. Technically, if that's the truth, when I drop this strong magnet down here, it shouldn't accelerate at G, it should accelerate at something less than G. Travis, come up here a second. Okay. I want Travis to demonstrate for us just a typical acceleration due to gravity. So grab this here, and then put this common everyday household resistor down there, and then try to just catch it when it comes out the other end. Okay. Okay, pretty quick, right? Do it again. And just boom. Okay, you guys got that? Kind of got how fast that is? It's pretty quick. Let me show you this. This strong magnet, when I drop it in here, is going to be opposed by little mini Lenz's law generated north poles. So it's not going to accelerate at G. It'll be a little bit less. Watch.
Oh my god. No way.
Oh. See that? I know. Watch this.
One more time.
Watch this.
Oh my god.
That's sick.
It is sick.
Holy.
In fact, I want to show you. I want to show you what it looks like, because you might be thinking that it's being caught up by the. Watch this.
Oh god.
I want to show you what it looks like.
Oh man.
Oh, that was.
Get this.
Nice
Get
shoes.
this.
Oh. Yeah, there we go. Oh.
Yeah, good enough.
Watch. Ready?
Oh, that is
Isn't that neat?
so awesome.
It's amazing.
See that? It just
That was
floats.
so cool.
It merely floats.
So
I know.
cool.
Isn't that crazy?
Holy
Look.
crap.
See-through copper.
Oh my god.
Right? It just floats
That's pretty cool.
like that. Okay? Why? Because you guys, as this thing falls, and you know what? Have you heard of magnetic braking on high-speed trains and so forth? That's what this is. Look, as this falls, there's a little current that flows around that generates an opposing magnetic field that keeps this thing from moving, accelerating at G. Yeah, Danny?
So if you had an even stronger magnet, would it fall slower then?
Sure. Yeah, you've got a weak little magnet, it'll fall, closer to G. Yeah.
If you have a strong enough magnet, will it accelerate upwards?
No.
Oh.
No, because when I drop it, it's going to have inertia, right? And
Oh,
the most it's going to do is travel at a very slow, constant speed down.
Okay.
Yeah, because there's always downward gravity. Does that make sense, you guys? Even the cyber people?
Yes.
Yeah.
Okay?
Can we do it again?
Want me to do it one more time?
Yes.
There she goes.
Oh my
That's
god.
very cool.
That's awesome.
Isn't that neat?
Mr. Wills, can I do it?
No.
That's so thick.
I'll take that.
Now, that's proof. That's proof right there that this actually does happen. All right? Lenz's law is real. And what it's telling us is that let me get my, what it's telling us is that when a north end is introduced here, the current has to flow so that the magnetic field opposes the changing flux that creates it. Okay? And that's a very huge thing. Okay? You need to be able to apply Lenz's law in this case. And so I'm going to give you guys an opportunity to do a couple of these. All right? Watch. I'm going to turn the camera back over to a book problem and have you guys try it. Oops. I want you guys to try this.
How'd you even do that? Just take a picture of this.
I want you guys to work on some. This is law yourself.
Dude.
Here it is. Here it is right here.
Whoa. Whoa, dude. Ah.
Yeah. Say it. No, you weren't.
This is embarrassing.
I'll smile. Why don't you like no smiles? Ow! You're so rude. He's mean.
You deserve it.
There it is. Okay. Now, look at this thing. Look at this thing. Watch this. This picture, don't be disturbed by the attempt at 3 dimensions here. Okay? If you want to imagine that the horseshoe magnet is facing you perfectly like this, and that this thing is just falling through the horseshoe magnet like that. Okay? Do you see what this is trying to do? So if I tell you that the magnetic field is more or less out of the board, you see why that is? As far as the loop is concerned, isn't the magnetic field north to south that it's going to be falling through out of the board? Okay, I want you to tell me what direction, as this thing's approaching the field, the current is flowing. Is it flowing what would be to us counterclockwise or clockwise? Work on that and see if you can work on it with your partners and see if you can answer the question, and then we'll go through it.
Yeah, because it goes like
You tell him, Jesseline.
I know. It's clockwise.
She's gonna watch this whole video.
Yeah, that's
Probably not, but
why are
whatever.
you taking this? I would never watch the whole video if I was them.
On your iPhone too, you're like, oh, can't put it down. I gotta like hold it. Take notes in one hand.
My arm hurts so much.
You want me to hold it? No.
I think I'm done.
I mean, she's not missing anything.